Okay, great. So thank you so much for the opportunity to speak here, and thanks to Chris for setting up solitons at work. Really a great idea. So I'm going to talk about accelerating solitons. This is based on work done in collaboration with Ilarion Melnikov and Costis Papageorgakis on these two papers here. This is a summary paper of the other one, the longer one. So what you're seeing here on the title slide are some animations constructed by a couple students here, Andrew Bowman and Quentin Hales. And that's work in collaboration with them and my colleague here, Doug Rutledge. It's not directly connected to what I'm going to be talking about, but it may be connected to a future direction that I'll mention at the end, which is exploring some numerics. But what these simulations are a wave packet, so you can see it here, colliding with a kink, and we're varying the momentum and the amplitude of the initial wave packet to see lots of crazy different behavior. And this is just solving the phi to the 4 equations of motion with those initial conditions. Okay, so let me start with a few slides of introduction to motivate what we're going to do. So we're going to consider topological solitons in good old Minkowski space-time. So the topological charge here determines different classes of boundary conditions which lead to finite energy solutions. And the topological charge labels different components of the field configuration space of finite energy solutions. And we're going to be mostly focusing on probably the simplest example in this class of theories. That's 2D linear sigma models with a single scalar field. So that's a function phi of t and x. So these theories have a field theory potential v of phi, and kink solutions exist when v of phi has distinct global minima. And a kink is a time-independent, energy-minimizing solution to the equations of motion. So we'll denote that classical solution by phi naught, and it approaches these two different vacua as x goes to plus or minus infinity. Now, the formalism to describe soliton states in quantum field theory goes all the way back to the mid-1970s. And for this class of 2D models that I'll be talking about, soliton states are labeled entirely by an on-shell momentum P. And they'll be denoted by this capital psi. So we're going to use a double angled bracket notation here for states in the Hilbert space of the QFT. Also in the 70s was laid down the formalism for describing semiclassical expansions of, for example, matrix elements, correlation functions. And that involves a small parameter, G. So we're going to restrict attention to potentials which have a scaling property where that small parameter G can be pulled out. Here the rescaled field is G times the original field, and the new potential doesn't depend on G. So this just allows us to pull a 1 over G squared outside of the action, and then it sits in the same place as H bar would. And so we can think of the G expansion as a semiclassical expansion. Okay, so although, you know, the quantum field theory with solitons in this class of models, although that framework is old and was laid out in the mid-70s, there are still some basic questions that remain unanswered to this day. So I want to focus on the case of soliton form factors. So that's just a fancy word for matrix elements of field operators, for example, the scalar field itself, between two of these soliton states. So here's a question. What is the leading, okay, so not exact results, just leading semiclassical behavior in G of this form factor at arbitrary momentum transfer? So not making any assumptions about P, the initial PI relative to the PF there. So the answer to that question is not known for non-integrable models such as phi to the 4 theory. At leading order in the momentum transfer, the form factor is the Fourier transform of the classical soliton profile, phi naught. But naive attempts to extrapolate that result beyond small momentum transfer fail when compared to explicit results that we know in integrable models such as sine Gordon. So why is that question so difficult? Well, let me relate it to a different question. So on the one hand, the soliton form factor that we want to study, or rather its Fourier transform over here, determines the amplitude for a soliton to absorb a perturbative particle and then carry on. That amplitude, though, is equal to the amplitude for a perturbative particle to pair create a soliton and an anti-soliton by crossing symmetry in the quantum field theory. So in diagrams, this equality between these two amplitudes, we could draw like this. So on the left, we have a perturbative particle coming in. I'll represent a soliton by these double lines. So there's my S coming in, there's my S going out, some initial momentum PI, final momentum PF. This is the same as, let's run this incoming soliton backwards in time and call it an anti-soliton. So S bar minus PI. So that's the statement of crossing symmetry applied to this amplitude. And that amplitude for the pair creation determines the leading contribution of virtual soliton-anti-soliton pairs to perturbative processes, like the propagator for the ordinary particle. So what this shows is that the form factor question that we started with is directly related to this question. Should we allow virtual soliton-anti-soliton pairs to run in loops when considering processes involving perturbative particles? So naively, so this question's been thought about for a long time. Naively, the answer is, well, yes, because of the optical theorem, or because of unitarity of the S matrix, we should allow all intermediate states to run in loops, and that includes the soliton-anti-soliton pair. Less naively, the answer, though, is no, because certain arguments based on the coherent state picture for soliton-anti-soliton pair indicate that such contributions are beyond the reach of perturbation theory. They should be exponentially suppressed in the semiclassical expansion parameter. And so therefore, we wouldn't consider them when we're doing a diagrammatic approach, which is only ever going to give us some asymptotic series in that expansion parameter for any given observable. But more recently, the answer has been, well, maybe. We should let them run in loops, at least in theories where the solitons in question could have small sizes. And here the size of the soliton would be with respect to its inverse mass. So this has been suggested in a few papers in relation to solitons possibly leading to contributions that aren't exponentially suppressed in certain non-renormalizable theories like instanton solitons and five-dimensional gauge theory. And this work by Bassard and Kleinschmidt has been about small black holes and supergravity. And they're actually running these things in loops using this exceptional field theory framework that they've developed. So it's been an interesting question in the past 5 years that's come up again. And my points are that this question is directly connected through crossing symmetry here by this analytic continuation to the question about the form factor that I started with. And there's no definitive answer. So the ideal thing would be, well, could we actually maybe compute that form factor and then by doing so, compute or at least bound the leading contributions, maybe in this class of 2D linear sigma models to show, okay, yeah, it is exponentially suppressed. Or even better, you know, what is that leading coefficient? So that's like the pipe dream. So today what I'll do is I'll describe a new avenue to approach the form factor question utilizing a new tool, the forced soliton equation. And so the plan is to review soliton quantization via the phase space path integral in this class of theories. And then we'll kind of summarize a little saddlepoint analysis, which leads to the forced soliton equation and what that says about these semiclassical soliton form factors. But I'll pause here if there's any questions so far.
Andy, could you just clarify? So in this expansion in G, is it right that the mass goes like 1 over G, but the size is of order 1?
So the mass goes like 1 over G squared in my convention.
Oh, right. Sorry, yeah.
Yeah, but then
What about the size?
Yeah, so for the like phi to the 4 theory, the size is order 1. Yeah, so the mass is like the mass of the perturbative particle divided by G squared, and then the size of the kink is of order the mass of the inverse mass of the perturbative particle, I believe. Yeah.
So when you mentioned small size in the last
That's
slide,
right. Yeah.
Is that
that wouldn't
is that
happen.
like introducing one new parameter?
Yeah, exactly. So yeah, so this would only happen for solitons where you, for example, the size was a modulus, maybe, like right. For the instanton solitons that can shrink.
Oh, I see. Okay, yeah.
Yeah, but you wouldn't expect it to be to be relevant in this class of models. The idea is just, can we do a computation to see what happens?
Okay.
Other questions?
Sorry, may I ask you, if suppose the coupling constant is running here?
Great question. Yeah. So I'm going to come to that on the next slide, actually. So we don't have to worry about that actually for this class of models. So let me do that. So we're going to stick in this land of 2D linear sigma models. This is the action. We're going to assume that this potential, so this is the classical action. The classical potential will assume that it's got multiple gapped minima. And then this is the M naught that I was just talking about with Nick. So it's the mass parameter controlling the mass gap to the perturbative spectrum in the theory. Now, when we go to the quantum theory, we need to relate bare parameters to renormalized parameters. And so for this class of models, it's a useful technical result that there exists a renormalization scheme such that to all orders in perturbation theory, the G is unrenormalized. And so we can just talk about G like we did in the classical theory. Meanwhile, the mass parameter does get renormalized, and the renormalized potential has the following form here. So this is an order G squared correction. And what we're doing is we're replacing the bare mass with a finite renormalized mass. This is the order G squared correction. And the basic idea of this is just that vacua, so quantum vacua are the classical vacua with the bare mass replaced by a finite mass, renormalized parameter. And that's all we're gonna really need to use from this. So when I talk about that classical profile phi naught, I mean a classical solution to the equations of motion, but with this finite renormalized mass. So for phi to the 4 theory, which is kind of the example you always want to keep in the back of your mind, this is the potential function, and this would be the classical kink. Here you see this integration constant representing the soliton position, which will play a big role. It's going to become the collective coordinate going forward. Okay, so with that, we can then construct the renormalized Hamiltonian. Here, pi is just dt of phi. And using that, we've got our kind of standard expression for matrix elements of local operators in this quantum field theory in terms of the Feynman phase space path integral. So let's kind of break this down a little bit. So this is our phase space measure. Here, we're allowing ourselves to describe the initial and final states by some wave functionals. And the notation here is meant to indicate, so for example, psi I of phi means a functional of phi at the initial time. And these could be quite general, but for example, if you wanted to study like the ground state, the vacuum in the theory, then perturbatively, these would be Gaussians in the field. Just like the Gaussian is the ground state of the harmonic oscillator. Here, this is e to the is in Hamiltonian form. And then by local operators, for example, we could consider just the field itself. And we're always going to just have operators at a single space-time point, Tx. So that's a kind of a general expression for a matrix element. What we want to do is we want to consider matrix elements between soliton states. So how do we define a soliton state? That's where we need to change variables. So to construct soliton states, we're going to change variables from the original phase space variables pi and phi to a new set. So one of the coordinates in the new set is going to be the soliton position, which is promoted to a dynamical variable, the collective coordinate. Capital P is its conjugate momentum. The remaining guys here, phi and curly pi, are the field theoretical fluctuations around the soliton, if you will. And I'll describe this second transformation in just a second. Now, to describe the change of variables, we need to introduce some notation first. So m naught is going to be the classical soliton mass given by this expression here. Psi naught is going to be the zero mode fluctuation. So that is just our usual L2 normalizable zero eigenvalue solution to the fluctuation operator around the soliton We have it because we have translation invariance. So this is the mode that we're going to remove and replace, if you will, with the collective coordinate. So the chi field and the curly pi field here are not unconstrained. They're not completely free. They're going to be required to be orthogonal to this zero mode. And we'll come to that in a second. Rho is the notation for the co-moving coordinate, little x minus big X of t. So we'll use dots to denote t derivatives and primes to denote rho derivatives. And then the single bracket notation is being used for the standard inner product here on rho. So with that, here is the canonical transformation. All right, so this is the original phi and pi field in terms of the new fields. So the coordinate transformation's not too bad, and it's kind of intuitive. Basically, we're taking the classical background and we're allowing the position of the kink to be a function of time, and then we're adding a fluctuation field around that. The form of the momentum transformation is dictated by the requirement that together this is a canonical transformation. The momentum transformation, notice here that it is spatially non-local. It involves integrals over rho of the new fields, but it is local in time. Now, I'll come to this comment down here. Oh yeah, let me describe that now. So what we want is for this transformation to preserve the phase space measure, and that's how this pi is determined, so that it does this, so that we don't get any Jacobians. Whoops, Jacobians when we change variables in the path integral. So the original phase space measure becomes the phase space here for x and p together with this new field theory phase space measure. And then here are the constraints that we mentioned. So these delta functionals are imposing that the new field fluctuations are orthogonal with that respect to that inner product that we had to the zero mode. So another way to say this is that if you were to compute the Poisson brackets of the original fields, then they'll be satisfied assuming actually Dirac brackets for the new fields, Dirac brackets because we're taking into account the constraints. Now, technically, it's a little bit more convenient instead of working with this chi field to just sort of absorb the background. And so the field I'm actually going to work with is curly phi, defined like this. And we'll still use pi. And now we're just going to rewrite things here. So since curly pi is orthogonal to the zero mode, I can replace chi prime with curly phi prime right here for free. And then down here, this actually simplifies a little bit to the derivative of the background soliton inner product with curly phi prime. And so that's the transformation that we want to then plug in to our expression for the matrix elements. Once we've done that, we'll be able to say what soliton states are. So here it is. This is taking that expression we had before. We're changing variables with the integration measure. Now our initial and final states are expressed in terms of the new coordinates, x and curly phi. The fact that the transformation is canonical is indicated here by the fact that we're preserving the symplectic form. HT is just the Hamiltonian in the new variables, except we've done one thing. We've exponentiated those constraints. And so we've added two new terms to HT. So we're writing those constraints as integrals over Lagrange multipliers of plane waves. just a technical convenience for what's to follow. The remaining terms in this Hamiltonian are the original Hamiltonian, just expressed in terms of the new variables. And in particular, we do have these spatially non-local terms right here, just coming from that momentum transformation. So now we can say what soliton states are, right? So those are particular wave functionals up here, right, of this form. So P tensor product psi naught is the ground state wave functional of the curly phi curly pi sector. And then here you recognize a standard quantum mechanics plane wave. And we're using the fact that we have Lorentz invariance or translation invariance in the underlying theory, so we know that states can be labeled by their momenta, capital P. And so that's what a soliton state is. And so now we can plug that in and we can start to take a look at this form factor. Before we do that, since things get pretty hairy here, let's take a step back and do some sanity checks. So let's look at a few different special cases. So first case is the adiabatic regime. So if we assume that the collective coordinate velocity x dot is small, and here I'm actually going to tie its smallness to my expansion parameter g, then we can do the following. So here what we're doing and what we're going to be doing in the following is we're taking our new field phi and we're always expanding it around a background. And we're doing it for all of our fields. I just didn't write them out, etc. So if we're working under this assumption that x dot is order g, then because the classical soliton mass is order 1 over g squared, that means P is order g inverse. And then taking the background to be the static soliton profile itself is a good approximate saddle point to the equations of motion. It's not an exact one, but if we plug in that approximate solution, then expand the Hamiltonian in these fluctuations, we get this result here. So what you see at the leading order is the mass. So that's order g to the -2. And then all of that non-local stuff here at leading order collapses down to p squared over 2m. And so, whoops, a little too far. That's your collective coordinate Hamiltonian. And that term itself is order g to the 0, or order 1, in g counting. Everything here is the quadratic order stuff in these fluctuations. All right, that's also order 1. And when we integrate it out by doing the Gaussian path integral, it leads to the one loop correction to the classical background soliton mass. And we'll call that one loop correction delta M. Now, because the classical profile here is not actually an exact solution to the time-dependent equations of motion, there are tadpoles. In other words, there are terms in this Hamiltonian that are linear in the fluctuations, and they come exactly from expanding out this denominator around that background. But because of our assumption about the order g behavior, they're actually suppressed relative to the terms I've displayed. And that's the primary reason for actually tying the adiabatic small parameter, the velocity, to the g, the semiclassical expansion parameter. So tadpoles are contained in here, in this approximation. Now, there's another approximation to consider where we expand around an exact solution, but an exact solution moving at a constant velocity. In other words, a constant momentum. So if we analyze the equations of motion in this curly phi sector, under the assumption that P, the soliton momentum, is constant, then we can actually solve those equations. And this was done by Gervais-Javicki and Sakita, whose formalism we've been following back in their original paper. And it's kind of, not surprising that this should be a solution. So what is this solution? Well, this is the classical profile, but the argument is being Lorentz contracted. So this is the boosted soliton profile. Gamma is just the Lorentz contraction factor, but expressed in terms of the momentum. Okay, so it kind of, because of Lorentz invariance, is not surprising that there should be a solution which represents a soliton moving with constant velocity, which is a boost of the static solution. But the way that this actually is a solution to these pretty non-trivial equations of motion in the phi sector is pretty neat. And so it really does work out. And so this is a solution to the phi pi EOMs, assuming P is constant. So that's kind of nice. And then you could do, perturbation theory around that solution. Now we really do have that the next terms are quadratic order and fluctuations. There's no tadpoles in here anymore, just the interaction terms. The leading order Hamiltonian becomes the relativistic energy. And now that is an order g to the minus 2. This is all order 1. And if you integrate it out, this was something that I don't think had been really explicitly shown in this formalism of Gervais-Javicki Sakita that we're following. But we did that one of the things we did in our paper. You do get the one loop correction to the relativistic energy here, specifically m naught delta m over square root p squared plus m naught squared, which is consistent with thinking of the relativistic energy, but using the corrected soliton mass and expanding that to first order in the correction. But this is still assuming P is constant, okay? Unfortunately, when insertions are present in the path integral, which is the case if we're going to study the form factor, it's not sufficient to assume P is constant when you're looking for a saddle point solution. Doing so would mean that you're only working to leading order in the momentum transfer. And so what we need to do is we need to analyze the equations of motion in this field theory sector for a general background P of T, not making any assumptions. So I should pause just for a second, see if there's any questions before we keep going.
Okay. Can I ask something? So
yeah.
So you said in the beginning that you didn't assume any smallness of the momentum transfer. So you only assumed to be perturbative in G, but any momentum transfer would be possible. But so I was kind of confused. If you go back one slide, your gamma shouldn't it be like 1 over 1 minus the velocity, and then you multiply? How did you get? Did you assume something?
No. Yeah, this gamma is consistent with the usual relationship that gamma equal, the usual formula.
Yeah, square root minus.
Yeah, 1 minus beta squared. And then you just, and then the usual formula for the momentum, P equals gamma m beta MV. So that will just come out. That's just a way to express the usual relativistic gamma. So there's no assumptions there. That's just the way to express the relativistic gamma for a particle of mass m in terms of the relativistic momentum. It catches your eye funny for me too, because I keep thinking that square root should be 1 over that square root, but no, that's actually correct.
Thanks.
P, yep, yep.
May I ask?
Yes.
One result of this approach is that you recover the Lorentz perturbatively. You recover the Lorentz invariance in the moduli space, right? Because you start when you do the usual moduli space, you somehow break the Lorentz invariance. You have the position of soliton, and now in this perturbative computation, you find out Lorentz invariance up to G square, and then you can, that's one of the, okay.
That's a nice result. And that was a big deal, like when Gervais-Jarecki and Sakita were first able to show this, because indeed you break Lorentz invariance explicitly with the change of variables, but the underlying theory, of course, should still have it. And so this is one way that you.
Thank you.
Yeah. Okay, so what we need to do though is this, because we can't assume that P is constant in our case for our form factor computation that we want to do. So there's no real tricks here. We're just analyzing the equations of motion, and you can solve for the other fields in terms of the coordinate field, and then you get an equation of motion for the coordinate background phi bar. It just took us some time to kind of figure out the right way to sort of phrase things and understand things, but no tricks. So I suppress the details and I just give you the result. So if you don't make any assumptions about P, then the equations of motion in the curly phi sector reduce to this one for the background phi. And this is the forced soliton equation. So it kind of looks like a wave-like equation here, but there's two rather interesting aspects to it. So you've got this forcing term, which is explicitly proportional to the derivative of the momentum. And you've also got this velocity, which is given down here. We call this the velocity functional because in the full theory, if you look at the equation of motion for the collective coordinated, it literally is the velocity functional in the full theory. But both of these things depend on the field, on the solution. So forcing term and velocity functional depend on the solution. So this is a highly, nonlinear integral differential equation that we're dealing with here. Also, the solution, besides solving this equation, we still need to impose the constraint on the solution. So this was the orthogonality of that original chi field, just expressed now in terms of the var phi. And you might think, oh, this is over constrained, but at least naively, it's not. So if you think of the left-hand side of this equation as a map from var phi bar into the space of functions on the real line, then the image of the left-hand side actually lies in the orthogonal complement of the span of the derivative. So in other words, there's one degree of freedom, which is not determined by this equation, and that would be fixed here. So a solution to this equation and this constraint then becomes a functional of this background P of t, which is arbitrary. So let's make some comments about this thing. So as I was mentioning, it's a nonlinear integro differential wave-like PDE. It describes a kink, soliton, undergoing acceleration with respect to an arbitrarily prescribed P of t. So in some sense, it's like a soliton analog of the Leonard-Vichert potential in electromagnetism. Now, what about initial conditions and boundary conditions? Well, there's a natural initial condition, which is that at some early times, we want to take the momentum to be constant, namely our initial momentum, pi. And so then the solution, or the initial condition we should start with, is the boosted soliton profile with that pi. Furthermore, boundary conditions at plus or minus infinity should be the usual ones that ensure finiteness of the energy. So from a physics perspective, at least, it's natural to make the conjecture that there should exist a unique global solution to this IVP for any given P dot, at least with a finite impulse, so that PF minus PI makes sense. Now, mathematically, the thing that kind of comes closest to this is it looks like it's a second order quasi-linear hyperbolic PDE. And there's a lot of very general machinery for existence of solutions to those types of equations due to Cato, Marsden, and Hughes. But because of the integrals that are involved, it doesn't seem like it quite fits exactly into any kind of pre-made package where we could just pull out some big theorem for this. So that could be an interesting math question. But what we can do for now is just assume that there is a unique solution and carry on a little bit further to see where we go with that soliton form factor. So last couple of slides, let's see what happens if we do that. So here we're going to assume we've got a solution to this forced soliton equation, and we'll expand in fluctuations, plug back into the Hamiltonian, expand. And then here again, the superscripts are telling us about powers of G. This leading order guy is just a functional of the background solution and therefore a functional of P, the soliton momentum. This guy involves quadratic terms and fluctuations, which in the saddle point approximation, we integrate out. And then we drop the higher order stuff. So we're going to define two things we're going to need to talk about that form factor. One is the semiclassical soliton effective Hamiltonian, where we carry out that saddle point integral in the var5, rpi sector. Remember, these were the ground state wave functions in that sector, which were part of the definition of soliton states. And so that's going to result in a semiclassical effective Hamiltonian for the soliton, which is a function of P. And then the other thing we need is we need to take our insertion that we want to do the form factor of, and we need to expand it in G as well. And we're just going to keep the leading order thing, which we get by taking the canonical transformation from the original variables and evaluating it on the background solution. And one kind of interesting thing to note here is that because of the translation invariance, this semiclassical insertion, which is now just a function of collective coordinate and its momentum, it only depends on the collective coordinate through this difference of the spatial x minus the collective coordinate position. That's going to be useful. So in terms of these two quantities, we can then write down the leading semiclassical behavior of the form factor that we started with. It reduces to a form factor in the quantum mechanics of the collective coordinate, but it's the quantum mechanics of the collective coordinate with respect to this really non-trivial effective Hamiltonian, right? Which comes about by plugging in the solution to the force-soliton equation. But this is what we have now. We have a quantum mechanics path integral. These are our initial and final conditions from the for the soliton state, and then we've got our semi-classical insertion. Now, you know, imagine this is some function of p and x over here. So instead of studying this guy, it makes sense to study a generating function. So in other words, we can recover that guy we want by expanding out, at least for nice OSCs, expanding out in a Taylor series, this thing, letting these functional derivatives act on these sources, k and f, to bring down p and little x minus big X. So what we're going to study is this generating functional. And the cool thing here is that because of translation invariance, x only appears here and here. And so we can actually carry out the x path integral, which results in a delta functional enforcing none other than Newton's second law. P dot is f, where f is the source here for x. That delta functional then lets us carry out the p path integral. So we can actually do this final quantum mechanics path integral. We get one extra p integral from the x integral. So we get a leftover delta function, an ordinary delta function imposing the impulse momentum theorem. So the momentum transfer is given by the impulse constructed from this source. And then we also learned that p of t should be a solution to Newton's second equation. So we could write that solution like this. And then that's what leads to this result here. So now we've evaluated that, that generating function, and we've expressed it as a result here. We now are taking our semi-classical Hamiltonian and evaluating it on the solution. So it now becomes a functional of f. And that's what this has to operate on. Also, because the k dependence here is pretty simple, we're actually able to evaluate all the k derivatives we need. And what happens is that that momentum argument of our classical profile becomes pi plus pf over 2. That's huge because that's a constant momentum. And that means that we actually know the classical profile, OSC, in terms of the boosted soliton profile. Because remember, a time-independent solution to the FSE is just the boosted soliton. So although we don't know much about this because it involves solutions to the force-soliton equation, we at least know the thing that has to act on it in terms of the classical soliton profile. So then finally, you can, by writing this as a series expansion and letting the derivatives act on either this factor or this factor, at fixed order of them acting on this factor, you can resum their action on the delta function here, and that results in a Fourier transform. So that brings us to this final expression, which I'll just put on the last slide here for our form factor. And so we got a sum over n. You're taking the nth derivative of this guy over here, and the coefficient is the Fourier transform of the nth derivative of the classical profile. So the f expansion of this thing over here is an expansion in momentum transfer because of the impulse momentum theorem. The leading order n equals 0 term gives the semi-classical form factor as the Fourier transform of the classical profile itself. So that recovers the original statement we had about the form factor. But then we've got corrections involving the Fourier transform of the derivatives, and they're weighted by that there. That's where the forced soliton equation comes in. So higher order terms involve the Fourier transform of derivatives of the classical profile weighted by the evaluation of this guy. So solutions to the forced soliton equation control the momentum expansion transfer through determining the dependence of this HSC on the momentum, and hence this force that we need to take derivatives with respect to. Okay, so let me just wrap up then with a few future directions. So kind of the natural first thing to do in analyzing this force-soliton equation would be to consider perturbation theory in P dot, which will lead to perturbation theory in the momentum transfer for that form factor. And so that's something we're looking at now. In the longer term, what we'd really like to be able to do is bound the behavior of the form factor, say at large momentum transfer, by considering that series I had on the last slide more formally. And here we can use Lorentz invariance. The fact that Lorentz invariance is only recovered from the whole series. Once you start including those higher derivative corrections. So that might relate neighboring terms in the series. Also, we can try to bootstrap by comparing against known results in integrable models like Sine-Gordon. We're also thinking about numerical investigations of solutions and somehow connecting them or relating them to the solutions I was displaying on the front slide, though not sure exactly how. And then of course, we'd like to extend this formalism and this forced-soliton equation to solitons and other theories. So near and dear to my heart is the monopole and Yang-Mills Higgs theory. So I'll stop there. Thanks, guys.
Fantastic. Thank you very much. Andy, let's think.
Thank you.
Very good. Lots of questions during the talk. I'm sure there's more questions out there.
Can I ask a question?
Please.
My name is Boris Malamet from the Tel Aviv University. The question is maybe indirectly relevant. In optics, there has been a lot of interest about self-accelerating modes, which are usually described by the airy waves, airy functions. Of course, they're very different from your setting because instead of the Lorentz invariance, they work with Galilean invariance. And actually, the fundamental solutions are solutions of the linear Schrödinger equation, but also people did a lot of theoretical and experimental work to study the nonlinear version of those self-acceleration modes. So the question is if you would see any similarity of your theory to that activity in optics.
I would love to. I mean, so when we first found this equation, we tried looking through the literature to see what had been done with any kind of soliton with an acceleration to see if people had constructed solutions, just to have something to connect to. So I'd be interested to get some references from you.
Okay, I can easily send it by email. Okay.
Yeah. But we couldn't come up with anything really concrete. So yeah, I'd like to connect it to something that's been done.
In terms of optics and BEC, there has been some theoretical work on self-accelerating solitons, definitely.
Cool. That's very good. Okay.
Excuse me, the Sine-Gordon is exactly dual to the massive kink. And if you may expect some ideas of duality, may help you to evaluate this non-perturbative contributions here, please.
Oh yeah. So the form factor in Sine-Gordon is known exactly, like both in momentum transfer and in G, because of some of the things you mentioned. So actually one has to do a little bit of work to take that exact result and then take its semiclassical limit to extract something that we can actually then compare against from within our formalism. So that's kind of an interesting little thing to do. But yeah, that I hope is going to really help us out, just to have something to compare against in that case. Yeah.
Can I ask a question? So I think a lot of people in the audience, they are interested in doing something what you have been doing in other models where you don't have necessarily have renormalizability. And so the one good thing in your scheme is that you didn't have to renormalize G. So G is not renormalized, but you had to renormalize M, and I'm not sure exactly what you did. And it didn't seem like you had in any of the steps, or maybe because of your very nice presentation, it didn't quite catch where you didn't need to introduce any counter terms, but maybe because you got rid of the tadpole just by counting the powers of G, so you got rid of the tadpole, where I would expect that you would get divergences and you would have to subtract off counter terms. But did you actually encounter divergences and had to deal with them in your treatment?
We did encounter the one. So when we evaluated the one loop correction to the background, and we explicitly evaluated it in the case of constant P and got that one loop correction to the energy. Yeah, you get a divergence, but it is, and you have to use a counter term which you've already determined from the perturbative sector analysis. So it's kind of a really non-trivial check that with the counter term you already know from the perturbative sector, you can cancel that divergence in the soliton sector.
That's very neat.
So yeah, that part's cool, but you're absolutely right that you would have to come up as soon as you want beyond tree level in the soliton sector too. You need to have control over those divergences. You have to have a prescription. You have to have a cutoff.
Yeah. That makes it pretty murky if it's not renormalizable. So there are some papers from I'm not sure, like 20 years or more ago, where they sort of try to sidestep this and just use the kinetic term where you can renormalize things. And if you do that about the soliton background, it goes completely haywire, because what the quantum corrections want to do is like to shrink the soliton, because that's what the kinetic term sees it wants to do. But the other term, if you ignore that, it doesn't really work out. I think you don't catch the correct physics.
Yeah, if you could send me those references, I think I know what you're talking about, but I'd like to see them again myself. But
okay,
the other, the other comment that just comes to mind is that I think the pipe dream about these comments about, non-renormalizable, like the only hope would be somehow in a maximally supersymmetric theory, you might just not have any divergences at all. And you would only see that happen by somehow including these contributions. But it's totally murky. I agree. Yeah.
May I ask one thing? My name is Sakai. When you mention this perturbation in terms of momentum transfer, there must be mass scale dividing this one. Is that the original mass gap or something else?
Actually to the soliton mass. Thank you for that question. Yeah. I forgot to mention that, but the momentum transfer expansion is momentum transfer relative to the soliton mass.
I see.
Yeah,
okay.
Because once you've integrated out to the field theory and you've gotten that soliton effective Hamiltonian, that's the only mass scale there. Yeah.
Okay. Thank you.
Thank you.
Can I ask you about what you can do with this force soliton equation? I mean, it seems to me that you could practically do things with it. I mean, maybe that requires some numerics. For example, P dot might be small. I mean, you did mention this on your last slide, which is still up. I mean, for example, P dot might be small, and then perhaps the most important feature of this solution is the asymptotic radiation field. You didn't sort of talk about that explicitly. I wonder how that connects with, the actual simulations you showed at the beginning, where there was some kind of small radiation interacting with the soliton.
Exactly. Yeah. That is exactly.
Is that what you're looking at? Is that what you're now looking at? This kind of sort of.
That's the plan. Yeah. And numerically, what we'd want to do is solve the force soliton equation, and then sort of subtract out the background kink itself, so that we can isolate that radiation. And then, yeah, and then integrate it against sort of the normal modes to see how it's dispersed among
So
the different.
can you just expand on that last remark? Integrate, what are you integrating against the normal mode? What, can you just expand on that?
Oh yeah, I just mean like take that solution and basically expand it in the normal fluctuation modes that you have around maybe like the boosted the constant motion soliton, for example.
Oh, I see. The continuum, you're talking now about the continuum spectrum of the linearized theory around, yeah. I mean, there's probably some numerical tricks for studying the radiation amplitude. I mean, you don't really need to do this orthogonality. You don't, you just look at the asymptotic oscillating field. Forget about the kink, which is far away.
Okay,
and just look at its frequency spectrum or something like that,
Yeah.
Because the theory linearizes.
Yeah.
Far away from the kink. You've got this sort of spatial separation for the kink. The kink is localized. So if you go far away from the kink, you can somehow forget about it. Just look at the linearized. But anyway, that would be work for small p dot.
Yeah.
But right at the beginning, you also talked about this interesting question about, kink anti-kink pair production. Are you anywhere near being able to say things about that?
No. I mean, what we still need to do is construct a numerical routine to solve the force. Like if we do it numerically, then at least we don't need to assume, right, small p dot anymore. So what we'd like to do is construct a numerical routine to solve the force soliton equation, and as a functional of a given p dot. So like maybe a nice thing to consider would be more or less a delta function impulse, or like a highly localized impulse in p of t, which is large though. Feed it into the force soliton equation and just see what happens numerically. So yeah, we're not there yet, but I would very much like to see what solutions look like, and if we can recover some of that behavior that I was showing you on the title slide. Yeah.
The title slide was about some other reverse process. It was about this meson fluctuation interacting with the soliton and causing some back reaction on the soliton.
Right. Well, yeah, I mean, that's the thing. I'm not exactly sure how to connect what I'm looking for in both pictures yet. But definitely the momentum transfer could originate from the meson hitting the kink. But yeah, how to set it up on both sides, I'm not so sure to make a precise comparison.